Alright, so we're going to work on a significance test for difference in proportions. And we're going to work through a problem and go through the state, plan, do, and conclude process that we need when presented with this type of problem. So let's look at this problem. We have, according to physics.org, Black and Hispanic females are underrepresented in STEM programs compared to non-STEM programs. A certain university would like to see if this is true for their student population. They took a random sample of 300 STEM students and found that 12 were Black or Hispanic females. A separate random sample of 500 non-STEM students had 75 Black or Hispanic females. So what we're looking at here is, do the data provide convincing evidence that Black and Hispanic females are underrepresented in STEM programs? And we're going to use a 5% significance level. So to talk about this in our state part, we talk about a parameter. Remember, our parameter is talking about the overall, in this case, P1 minus P2, right? We're talking about a difference in proportions because they gave us a sample size and the amount that were Black or Hispanic from each of those sample sizes. So we'd have a proportion. So our parameter, again, we're going to be looking at P1 minus P2. All right, and what does that mean? What is that telling us? Well, that is telling us the true difference in proportions of Black and Hispanic females in the STEM and non-STEM program. All right, so again, the true difference in proportions of Black and Hispanic females in STEM and non-STEM. Now, let's talk about our statistic here, right? So our statistic is simply going to be our P1 hat minus our P2 hat. So in other words, the same proportions from P1 minus P2. So for this, let's calculate that. Well, for P1, we're talking about the setup for STEM, right? Because STEM is your P1. So we'll just go ahead and label that so that we know what we're talking about. And P1 is STEM, and so therefore it says we had 12 out of 300. So 12 out of 300, and that should give us 0.04. And then for our P2, we had non-STEM, and that gave us, as you can see, we had 75 out of 500. And that should give us 0.15. So now we're going to take these two values and subtract them. So we have 0.04 minus 0.15. And that should give us a value of negative 0.11. So our statistic right there is negative 0.11. I'm just going to put a box around it so I know where to look and find it in the future. Okay, and our significance level, well, they give us that. Significance level is right here. They actually tell us this time. So our sig level here is 0.05. Now let's talk about our hypotheses, in which case how to develop these guys, right? So our hypotheses in this case, we're going to look at for our null hypothesis. They're talking about to see if there is a difference, right? So our null hypothesis should mean that there is not a difference. So if it is not a difference, then we'd be simply saying we have P1 minus P2 equals 0. In other words, if there's no difference, well, then that would equal 0 then, right? Now for our alternative, we're going to talk about saying that it says if they're underrepresented. So in other words, the difference should be less than 0 because we have P1 minus P2. So therefore, we should have a less than 0 value for the alternative because you would have a small number for your P1, in which case we had 0.04, and you have a larger number for your non-STEM, which was P2, which we did in our sample as well, 0.15, and gave us a negative 0.11. All right, so let's watch another little sample video exercise here to maybe help explain that on how to develop these hypotheses a little bit easier.
Hey, this is Jason Molesky. In this example, let's review stating hypotheses. Researchers designed a survey to compare the proportions of children who come to school without eating breakfast in 2 low-income elementary schools. A simple random sample of 80 students from School 1 found that 19 had not eaten breakfast. At School 2, a simple random sample of 150 students included 26 who had not eaten breakfast. More than 1,500 students attend each school. Do these data give convincing evidence of a difference in the population proportions? Let's state appropriate hypotheses for a significance test to answer this question, and be sure to define any parameters you use. In this case, we should carry out a test of the null hypothesis P1 minus P2 equals 0 against the alternative P1 minus P2 is not equal to 0, where P1 equals the true proportion of students at School 1 who did not eat breakfast, and P2 equals the true proportion of students at School 2 who did not eat breakfast. Now, if a question like this comes up on the AP exam, or when you carry out a hypothesis test on the AP exam, you'll want to remember to always use population symbols and language when writing your hypotheses. Never write them in terms of your samples.
Okay, so hopefully that example helped explain how the null and alternative hypothesis is developed to move forward on more problems. All right, so now that we've got our state plan taken care of. So again, when you write out this, the state part has to be listed all of this. State is parameter, hypothesis, significance level, and your statistic. You'd have all those labeled in your state part. All right, so for number 2 here, or for the second part, I should say, we have plan. So in plan, we're going to name the procedure and check conditions. So for this, what's the name of our procedure? Well, again, think about it. How many samples do you have? It's proportions, so we're going to talk about z's, and we're talking about a difference in proportions. Okay, so let's name that then. We can simply say that we have a two sample z-test for a difference in proportions. You don't have to write out all of that as you would read it. So two sample z-test, and then you simply write for, and then as we're talking about, P1 minus P2. There you go. Two sample z-test for difference in proportions. So instead of just saying like we did when we did one sample z-test for proportions, we're talking about a two sample z-test for a difference in proportions. All right, so now let's look at our conditions. Now for the conditions, again, as we've done with every one of these, you have to make sure it's random. Okay, let's see if it's random to begin with. We can go back to look at the problem itself. Now it says in here they took a random sample of 300. They took a random sample of 500. So a random sample of 300 STEM and a random sample of 500 non-STEM. Well, all you need to do is write that out. Took a random. I took a sample of 300. Then we took a random sample of 500. In which case, both of those check off, right? Because it's given to us in the problem. It states that we took a random sample of both those. So we're good. Check mark. Good to go. Now another one that we always need to check on as well is dealing with our 10% condition. All right, so our 10%. In this case, we have 300 STEM students, and we'll see that's less than 1/10 of all STEM students, right? And I would definitely think so, because there are more than 300 STEM students in the United States, all right? And same thing with this on 500 non-STEM students. So there are definitely more than 500 non-STEM students based on the population of, looks like we're talking about America here, right? So we got our 10% condition is check, our random is check. Now the last thing we got to deal with. So now we need to see if we can have an approximately normal shape that we can draw here. And to do that with proportions, we worry about looking at large counts. So we're looking at large counts. Now, as we talked about in the previous lesson, where we're dealing with confidence intervals, and we had to deal with large counts, we still had to do it for both samples. So we're going to do it for both samples here for our difference in proportions. So we had 300, our sample size, times our proportion of 0.04. All right, so that's n times p. And then we're going to take n times 1 minus p. And we're going to simply say 300 times 0.96. Okay, so this first one up here, this equals 12. And this equals 288. Now we're going to do it for our second sample as well. So we're going to need to take 500 times 0.15. Now we're going to take 500 times 0.85. All right, so 500 times 0.15 should give us 75. And times 0.85 should give us 425. Then you can simply write that this is all greater than or equal to 10. So it all checks off. We're all good. So all our conditions are met. So now let's look at talking about the do part. Let's get this taken care of here. So for the mean, like we're talking about proportions. Well, we're talking about the mean of proportions, okay? So if we're talking about the mean and the difference of proportions, right? Just as we had talked about, we said the mean of a one sample, right, was equal to the proportion. Okay, well, it's going to be the same thing, but we're talking about the difference in the proportion, okay? So we have to think about that for a second. This is going to be P1 minus P2. Well, what do we say our null hypothesis was? We said P1 minus P2 equals 0. So if it equals 0, that's what our P1 minus P2 is, because we're saying there shouldn't be a difference between them, right? So therefore, the mean for the difference of proportions is 0. All right, so now let's look at our general formula. So for our general formula, again, we're talking about our test statistic. We're trying to figure out here, and that's going to equal the statistic value minus our null all over our standard deviation. So now we need to write a specific formula. Our specific formula, our test statistic, will simply be our z. Okay. Our statistic up top is going to be our p1 hat minus p2 hat minus our null value, which you shall see that it's a 0, but we're going to write out p1 minus p2. And we're going to divide it by our standard deviation. Now, the next thing we got to worry about this on our standard deviation is that the standard deviation for this style problem, because our p1 minus p2 equals 0, we must use a pooled proportion or combined proportion is how they like to notate it as well. So for that, we're going to write this out. I'll write it out, and then I'll show you how to calculate your combined proportions, okay? So this is going to be simply saying that you're taking your PC hat, so your combined proportion, right? So you're going to do that and take 1 minus that all over the first sample size. Then you add this. Again, you're going to use your combined proportion times 1 minus combined proportion all over your second sample size. Now with doing that, to calculate your pooled proportion or combined proportion here is simply going to be by taking the two success values in this case, which were 12 and 75. So we took 12 from the STEM group that were Black and Hispanic, and we took 75 from the non-Hispanic and Black. I'm sorry, non-STEM that were Black and Hispanic. Got tongue-tied there. All of this is going to be divided by then the total of the overall sample sizes. So we took 300 from the STEM and we took 500 from the non-STEM. All right, and that should give us 87 on top over 800, and that will give us 0.109. So now that we have that value of our combined proportions or pooled proportions, we're going to simply figure out what our standard deviation is to begin with before we actually start plugging in for the work part. Let's go ahead and just figure out what our standard deviation is to calculate this. So to do that for our standard deviation, we simply can just write out standard deviation for this p hat 1 minus p hat 2 is going to be square root and then fill in the blanks for our variables here. So we got 0.109, it's 1 minus 0.109 all over our sample size of 300 plus, and then we're going to do the same thing. 0.109 times 1 minus 0.109 all over our sample size of our second sample of the non-STEM, which was 500. And what does that give us? So that gave me 0.02279. All right. So now, when we're doing this for the actual work part over here, actual work part of this side, I know we kind of got that going a little overwhelmed, but we'll do the work right here. So the work part for our z-score here, we're going to simply take our p1 hat minus p2 hat, which we got for a value of negative 0.11, so a negative 0.11, minus our null, which is 0, all divided by 0.0227959. And for that value, we should get negative 4.833. So we got a z-score of negative 4.833. Well, that's pretty far out there on the tail. So then we should expect, your tongue tie there, we should suspect that we should have a very small p-value because that's really far away from the mean value, right, of 0, negative 4.833. Okay. So let's go ahead and draw this. Since we have these values, let's go ahead and draw this guy out. So let me get my pen over here. All right. So we draw our picture here. Okay. And we're going to say we got 0 right there. And we're going to say that we're going to use n 0 for our mean in this case, and our standard deviation that we calculated right above where I'm writing here, which is 0.02, we'll say 275. Now let's write it all out since that's what we used. In which case then we have a negative 4.833. Well, I'm going to write it just right here. So negative 4.833. And we're saying less than. So we'll shade this way, going to negative infinity. All right. So again, test statistic is right here. That's what we're looking at right there. So now we need to do our p-value. To do your p-value is menu, if you have a TI Inspire, it's menu 652. So you should get a normal CDF. You write that out. You write that out even if you're using the Desmos calculator, just write out norm CDF because you're going to do the same thing on there. In which case, then you're going to talk about your lower bound, which would be negative infinity. Your upper bound will be negative 4.833. In this case, we used our z-score value, so our mean is 0. And our standard deviation is 1 for that to calculate for your p-value. So now that we've got that put in there and you calculate that out, I got a very small number. I got 6 times 10 to the negative 7th. So we're saying 0.0000006. So I can write my 6 better. There we go. So a very small number, and this is equivalent. You could also simply say 0 because that is a very small number, right? Very small number. All right, so now we know we've got that. So what does that tell us then? Before we even move forward with that, our p-value is really low. So if the p is low, reject the hoe. So 0 is less than our 0.05. So we're going to reject the null. So reject the null. So now you've got the do part done. Now all we need to do is our conclusion, right? Conclude this up, or write this up. So now it doesn't have to be verbatim this type of sentence structure every time, but very similar as far as stating what the context of the problem is. In this case, the difference in proportions and what the proportions are, what the probability is you got, and what you're going to do, whether you reject the null or fail to reject the null. So again, let's read this. Assuming there is no difference in proportions, remember our null hypothesis, P1 minus P2 equals 0. So there's no difference in proportions of Black and Hispanic females in STEM and non-STEM. There is a 0.000006 probability, or you could just put 0 there to begin with, probability of getting a difference in sample proportions of our statistic right there of negative 0.11 or farther purely by chance. So again, you don't even have to put all this in here. You could have simply just said 0. Okay, because you have a 0 probability of getting a difference in sample proportions of negative 0.11 or further purely by chance. Then simply state we reject the null, or we fail to reject the null, and throw in the statement either you have statistically significant evidence or you do not have In this case, we have just statistically significant evidence against the null. So therefore, we reject the null. Okay. What I underlined there is exactly what the readers are going to look for when they're grading your test. Like myself, when I'm grading the test, I'll be looking for this type of wording to see if you put that in there. So again, let's go over a couple examples out of the book, and therefore you can get a little bit more practice with this.
Hey, this is Jason Molesky. In this example, let's carry out a significance test for the difference between two population proportions. Researchers designed a survey to compare the proportions of children who come to school without eating breakfast in two low-income elementary schools. As we saw in our previous examples, a simple random sample of 80 students from School 1 found 19 had not eaten breakfast, while at School 2 a simple random sample of 150 students included 26 who had not had breakfast. And recall, more than 1,500 students attend each school. Do these data give convincing evidence at the alpha equals 0.05 level of a difference in the population proportions? Well, let's start by stating our problem and stating our hypotheses. As we saw in a previous example, our hypotheses are the null p1 minus p2 equals 0 against the alternative p1 minus p2 is not equal 0. We're simply looking for a difference, so we'll do a two-sided test. And we defined our population proportions as such. If the conditions are met, we should perform a two-sampled z-test for p1 minus p2. Well, we were told the data were produced using two random samples of 80 students from School 1 and 150 students from School 2. So our random condition in this case is met. Now the researchers are sampling without replacement, so we have to check our 10% condition. Note there are at least 800 students at School 1 and there are at least 1,500 students at School 2 as given by the problem, so the 10% condition is met. Finally, for large counts, we have to check the counts of successes and failures and ensure they're all at least 10. And in this case, when we look at our sample size times p hat 1, we have 19, we have 61 failures, 26 successes in sample 2, and 124 failures in sample 2. All are greater than 10, so our large counts condition is met. Therefore, we know that our sample sizes and our sample proportions are as such. 19 students out of the 80 at School 1 had not eaten breakfast for 23%, and 26 out of 150 sampled students had not eaten breakfast at School 2 for a sample proportion of about 17%. Our point estimate for the difference then will be the difference of those two, or 0.0642 when we subtract sample 1 minus sample 2 proportions. Now the pooled proportion of students who didn't eat breakfast in the two samples is found by adding the total number of successes and dividing by the total of the two sample sizes. 45 successes total over 230 students sampled total across the two buildings gives us a pooled proportion of 0.1957. We'll use this when calculating our test statistic, and as we can see, our observed sample difference was 0.0642. We'll use the pooled proportion when figuring out the standard error, and we get 1.17 for our total test statistic z. Now, using table A or normal CDF, our desired p-value is twice the probability that z is greater than or equal to 1.17. We can look that up in table A and subtracting that from 1 and multiplying out, we have a p-value of 0.2420. Now, because our p-value 0.2420 is greater than our significance level, we fail to reject the null. There is not convincing evidence that the true proportions of students at the two schools who didn't eat breakfast are different. Hi, this is Jason Molesky. In this example, we'll take a look at performing a significance test for an experiment. Now, high levels of cholesterol in the blood are associated with higher risk of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? The Helsinki Heart Study recruited middle-aged men with high cholesterol but no history of other serious medical problems to investigate that question. The volunteer subjects were randomly assigned to one of two treatments. In the first group, 2,051 men took the drug gemfibrozil to reduce their cholesterol levels, while in the second group, a control group, 2,030 men took a placebo. During the next 5 years, 56 men in the gemfibrozil group and 84 men in the placebo group had heart attacks. We want to know if that difference is statistically significant at the alpha equals 0.01 level. Let's start by stating our problem. We hope to show that gemfibrozil reduces heart attacks, so we actually have a one-sided alternative. We'd like to show that the proportion of individuals who have heart attacks in the group taking the drug is less than the proportion of individuals in the placebo group who would have heart attacks. We can write these hypotheses two different ways. We can write them either as statements with the differences in proportions, or we can do a more straightforward approach just comparing the proportions. In either case, our null hypothesis is a statement of equality. Either the difference between proportions will be 0, or we can write it as P1 equals P2. For the alternative, it's one-sided, so we want to show that the difference will be less than 0 or that one proportion is less than the other proportion. In this case, we'll define P1 to be the actual heart attack rate for middle-aged men like the ones in the study who take the drug gemfibrozil, where P2 is the actual heart attack rate for middle-aged men like the ones in the study who take only a placebo. So because of the way we've defined them, we want to show that P1 is less than P2, or the difference, P1 minus P2, is less than 0. And again, we'll use alpha equals 0.01. Now, if the conditions are met, we'll perform a two-sample z-test for P1 minus P2. Well, we were told the data come from two groups in a randomized experiment, so the random condition is met. The number of successes, in this case, a success is actually defined as individuals having a heart attack, and the number of failures in the two groups are all greater than 10, so the large counts condition is met. With those conditions met, we can perform our calculations. The proportions of men who had heart attacks in each group can be calculated. For the gemfibrozil group, p hat 1 is 56 individuals who had heart attacks out of 2,051 for a sample proportion of 0.0273. And in the placebo group, 84 individuals out of the 2,030 had heart attacks for a sample proportion of 0.0414. Now, our pooled proportion of heart attacks can be found by taking the count of heart attacks in both samples combined divided by the count of subjects in both samples combined. In this case, a total of 140 individuals had heart attacks out of the total of 4,081 that were sampled, or in the actual experiment, I should say. That's a pooled proportion of 0.0343. For our test statistic, we use our test statistic formula. We observed a difference between our sample proportions. We use our pooled proportion in our standard error calculation, and inserting all of the appropriate information and performing the calculation, we get a z-score of -2.47. Now, using table A or normal CDF, the desired p-value in this case will be 0.0068. Now, because our p-value is less than 0.01, the results are statistically significant at the 0.01 level. We can reject the null hypothesis. In context, we have convincing evidence of a lower heart attack rate for middle-aged men like these who take gemfibrozil than for those who take only a placebo.
All right, so after watching that, hopefully you got a better understanding with this. Again, let's just go over the big ideas to take away from this. Again, in your hypotheses, you're going to take away that your null hypothesis is going to be your P1 minus P2. It's going to equal 0. Your alternative, depending upon the problem setup, it's your P1 minus P2, and it could be anywhere from greater than, less than, or not equal to. It could be a two-sided. Okay, so greater than, less than, or not equal to 0. Then the key thing that we learned is a difference that we haven't talked about before is your combined proportions or your pooled proportions, in which case that's going to be both portions combined. Okay, so in which case you take the successes from both samples on top, add them together, and then you take on the denominator, you're taking the sample sizes of both of them, adding them together. Also, too, we talked about our mean of our difference of proportions of our p hat or p1 hat minus p2 hat, which is the same thing as saying your p1 minus p2, which is in our null hypothesis equals 0, right? 0. So your mean is going to be 0. So when you're drawing out your picture, that's what you're going to have. You're going to have your normal curve, your n, your 0 for your mean, and then you're going to have your standard deviation of your p hat 1 minus your p2 hat, okay? Which you will calculate as we did in our do part. right? And then also label 0, and then you can put whatever value you get for your z-score there. Again, to calculate your standard deviation for this difference, remember, you cannot just use P1 and P2 in there like we did for our confidence intervals. To calculate the difference in proportions for significance test, because it equals 0, you have to use your combined proportions. So in this case, you're taking your combined proportions, 1 minus that value, all over your first sample size, and then doing that again, adding it to it again, but over your second sample size. Okay. 1 minus combined proportions over the second sample size. All right, so if you've got all that down and grasp what to do with those problems, you're all good. So I hope you learned a little bit of something, and I'll see you next time.